Welcome to the fourth presentation in the sixth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the fourth webinar in our sixth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the sixth series will be distributed through the IAS mailing list, Twitter feed, and LinkedIn page. Today's webinar will be given by Dr. Mijndert Van der Spek at Heriot Watt-University in the United Kingdom. I am Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Bhupesh Murugapan at University of Alberta in Canada. We're required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. We have also started a LinkedIn group, which can be found by searching the International Adsorption Society. Please help us expand our YouTube channel by liking this video and subscribing. We would like to remind the attendees of the 15th Fundamentals of Adsorption Conference that is being held this year in Porto, Portugal, between May 18th and 23rd. Additional information can be found at the URL given on the slide. If you plan on attending, the organizers have asked that you please register as soon as you're able to. We look forward to seeing everyone there later this year. I'll now hand it over to Bhupesh Murugapan, who will moderate the YouTube Q&A.
It is my pleasure to welcome Dr. Mijndert Van der Spek to today's webinar session. Mijndert is an associate professor at the Heriot Watt-University. He has received training as an energy systems engineer and policy analyst at the Delft University of Technology. Mijndert has also worked with the Royal Dutch Shell in the Netherlands, initially with the supply chain optimization team, and then as a process technologist at the polyols plant. He received his PhD from the Copernicus Institute of Sustainable Development, focusing on techno-economic and environmental analysis of CCS and CCU technologies. Mijndert was a postdoctoral researcher at ETH Zurich, gaining experience in CCS process design and CCUS system analysis. Mijndert's research focuses on developing methods and tools to assess climate change mitigation technologies. He is driven by improving the ways we undertake such assessments to make them relevant to policy and decision makers. Besides his work on process and system modeling, his team focuses on combining advanced measurement methods and process modeling to understand and describe CO2-water binary interactions on solid sorbents. During this webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Mijndert Van der Spek again and pass over the presentation to him.
Many thanks indeed, Bhupesh. Good morning, good afternoon, and/or good evening to everybody. Can everybody hear me well?
Yes.
Yes.
That's fantastic. Then I'll try and share my screen. Is my screen sharing well?
Looks good, yes.
The new thing is that okay, I need to go Forward. There we go. So I'm extremely pleased to be invited by the International Adsorption Society, and thanks very much, Nicholas, for the invitation to speak to you all today. And I'll be speaking about the complexities of water and carbon dioxide coadsorption onto chemisorbents for carbon capture. And obviously, as a scientist, I do not work alone. So there's a couple of people that I would like to acknowledge for their contributions, and that's first and foremost my colleague Susana Garcia, John Young, Enrique Garcia Diaz, Katja Piscina, and then from Berkeley there's also Ah-Young Song, Jeff Reimer, and you know, also the wider Jeff Reimer group. And I'm sure I'm forgetting people, but please don't feel bad. I do think about you from time to time. Maybe I just wanted to start with a little bit of background, and you know, why am I speaking about CO2 adsorption, and why am I speaking about CO2 and water adsorption? And what I'm showing to you right now is a stylized pathway of greenhouse gas emissions. And those are greenhouse gas emissions over time. This is a figure that goes from the year 2010 to the year 2100. So that's at the end of this century. And what we're hoping to see, of course, at least everybody that cares about climate change, is that the greenhouse gas emissions are going to peak, and that should happen really, really very soon, hopefully. And after the peak, it should go down, of course. And what we should even see, and that's depicted here by this black line, is that we reach at some point net zero greenhouse gas emissions, and at the end of the century even go towards net negative. And that is really needed to stabilize the climate at let's say 1.5 degrees or 2 degrees above pre-industrial levels, right? So when we start to emit CO2 in very large numbers. And now CO2 capture is something that can help reduce the emissions from, for instance, industrial plants that are really hard to decarbonize. Think, for instance, of cement plants, steel plants, waste to energy plants, etc. And also power plants, in the case we need fossil-based power as, for instance, as backup for all the intermittent renewables. But likewise, what you see in this graph is that, you know, we'll probably never get rid of all the anthropogenic emissions, and therefore we need to compensate that in a way by negative emissions, and even at some point these negative emissions need to become larger than the let's say the positive emissions from industrial and human activity. And for that we can also use direct air capture, which has generated a lot of attention and even investment recently. So you're both mitigating CO2 emissions as well as removing CO2 from the atmosphere rely on CO2 capture, and adsorption is very well suited for that. So that's in the context of this lecture, right? So we capture the CO2 either from flue gases or directly from the air. The CO2 partial pressure is quite low for flue gas, so we're talking about 0.03 to roughly 0.2, maybe 0.25 bar. And if we're talking about direct air capture, then we're talking about very low partial pressure. So we're talking about 4 to the power minus 4 bar. So, you know, that's difficult to capture. And then really important is that flue gas and air is humid, and relative humidities, for instance, across the globe vary between 10 and 100%. Even in deserts, there's usually some humidity. Flue gases, when they enter a capture plant, are usually saturated in water, so they're about 100% relative humidity, right? So humidity is critical, and you know, to my mind, really insufficient research has gone into the effects of water on adsorbent and adsorption processes. Now, you know, why is this important? Well, I mean, different adsorbents perform differently under humidity. So what I'm showing here on the left is a plot that shows the CO2 enhancement factor as a function of the CO2 pressure and as a function of relative humidity. So you see here crosses for 30% RH and for 55% RH. And you see that at very low partial pressures, actually water enhances quite significantly by a factor of 2 about the adsorption of CO2. And what you also see is that for this particular material, which is a polymeric resin, you see that as you increase the CO2 partial pressure, so you move towards the right on this diagram, then the enhancement factor moves, to around 1, right? So there is no enhancement anymore. So the water doesn't do much. But this is for a polymeric resin that's functionalized with amines. But conversely, if you look, for instance, at a zeolite, which is a material that is, kind of the working horse of the adsorption community, that really suffers from water for most zeolites. So as you start to increase the humidity, the adsorption isotherms, and this is really nice work by former colleague Max Hefty, that really starts to go down. So if you have a dry zeolite, then you have a really nice uptake, and this is even up to 10 bar. But then if you go down, if you add humidity, so then you basically lose virtually all CO2 uptake capacity. And we also know why. The water just likes to coordinate very, very nicely with some of the metals in the zeolites. Now, this is just another slide to illustrate why humidity is important in process design. And as CO2 capture scientists or technologists, we often look at 2 measures. I mean, first and foremost, we want to have nice purity and recovery of the CO2 because we need to put it on a pipeline, so we want it to be pure and we want to recover as much as we can. But then to secondary measures, or maybe I should call them primary, are the productivity. So how much can you capture with a given unit per day or per year or per unit of time, and how much energy is needed to do that, right? And so here in this graph, that's expressed as work equivalent. And these are results for a direct air capture design with levitite, which is a polymeric resin. And you see here that this Pareto front gives the productivity energy combinations, the feasible combinations, when you don't include any coadsorption in your model, right? So you exclude that from the description of your performance. And then here you see the Pareto fronts for the situation where you do include coadsorption in your model description. So here we had 2 different models, and you see that they are very close together. But what you also see is the difference with not describing coadsorption is really huge, right? So you get much better productivity and also lower energy consumption if you include the effect of water. But that's only for this adsorbent, and every adsorbent has its own either love or hate relationship with water. Okay, so then science wouldn't be science if there weren't challenges to solve or to overcome, and there are 3 main challenges. So the first one is measuring water CO2 coadsorption. Extremely difficult. Very few of such coadsorption measurements are reported, and given the headache that I end up going home with most every day, I can understand that. So, but okay, so still it needs to be done ideally. Then second is understanding the coadsorption mechanisms. So, do we have competition between water and CO2, or do we have enhancement? Is there no effect? And then if there is an effect, then we want to understand why, of course. And then third is modeling these mechanisms. And I'll briefly touch upon all 3 today. So let's start with the coadsorption measurements, and these are the things that give me the largest headaches. So generally, there's a choice of 2 methods. The first one would be dynamic breakthrough experiments, and it's talking about working horses in terms of lab methods. Breakthrough methods are really a working horse of the adsorption community, right? Many of you will have used them, or will have such experiments in the lab. And what they do allow is varying CO2 and water concentrations and temperatures. So that's really nice. You can dose CO2 and water in different concentrations at different temperatures, and usually you'll have also some kind of a vacuum system, so you'll be able to do that. You'll be able to regenerate your sorbents, etc. What they also allow is measuring the effect of water on CO2 and vice versa. So that's really good, because it can also be that, not only CO2 can be affected by water, but vice versa, the same can happen. What it needs, however, is integration of the breakthrough curves to find the uptake, right? How much of each adsorbate is adsorbed onto the surface of the material. And this creates a possible source of error. And finally, what can happen, and especially in the case of chemisorbents, is that such systems can present insufficient outgassing capabilities. And for chemisorbents, you need to draw really a very deep vacuum. So you need a turbo pump. You need a low volume system, and then you also still need to heat it to regenerate them fully. And not all the breakthrough rigs have that ability. And then on the other hand, there's gravimetric methods. I mean, they can also be volumetric, but I prefer gravimetric. Those can be static or dynamic adsorption experiments. They also allow variation of CO2 and water concentrations and temperatures. And they allow measuring the effect of water on CO2 or vice versa, but not at the same time. Unless, of course, you would equip these machines with a composition probe and very accurate flow metering and control. So then it would be possible. And then what they do allow is a direct measurement of total uptake. So that's really great. You get a direct mass out of your system, but then you still have to allocate that to the different adsorbates, and that can be an issue. And in principle, these kind of systems can be fully automated. So if they're working, they're plug and play, but if they're not working, they're a headache. So we use what is called dynamic vapor sorption technology, and we use it for coadsorption experiments. And we started with that about 5.5 years ago. And here you see a figure of such a system. And basically what you have is you have a vapor or a gas and another vapor or another gas flowing into a measurement chamber where there's a sample pan. On the other side, there's a reference chamber. Both are connected to a very sensitive microbalance. So whatever you dose into the system continues to flow outwards towards a rotary pump. Or it can be any kind of vacuum pump, and it has a turbo pump for outgassing. So that's really nice. And the reason why it has a sample chamber and a reference chamber is because it's a flow system. So you don't want any disturbances of the flow to your sample. So if you have this reference on the one side, both pans see the same amount of flow, and therefore the flow doesn't disturb the measurement. So you don't have any buoyancy effects, or that's at least accounted for. These systems, they do, or our system works on the basis of vacuum, and so that it requires holding a very deep vacuum, and that's a challenge. And I'm going to show some of that later. Now let's look at kind of a measurement profile for a coadsorption measurement that went really well, right? So what you see here is a graph, and you see on the horizontal axis we have time in minutes. And then on the vertical axis, we have the mass of the sample in the sample pan. And this is an experiment done at 25 C and for 30% relative humidity. And what we do first, and this is for a polymeric resin, is that first we dose water and we let the water equilibrate. And we need to do that because we need to close the mass balance. So if we would dose water and CO2 together, we wouldn't know which would contribute to which amount of the mass uptake. So we need to disentangle that. And therefore we dose the water first. And then in different steps, we'll do the CO2 adsorption. And sometimes these steps are really small. So for instance, this is where one step ends, where my red pointer is now. And this is where a next step ends, and a next step, and a next step. And these kind of measurements, we often, because we also interested in direct air capture, so we often try to go to very low concentrations of 200, 400, 600 ppm, and that's why some of these steps are so very close together. So this is an experiment that went well, right? We see nice equilibration. we see nice plateaus at the end of each step, so we can very accurately assign an uptake to that. Now, also sometimes the experiments don't go quite so well. So let's look at another experiment, and this one was on also 25 degrees C, but at 80% relative humidity. So the humidity is much higher. And what you need to know is that at 80% relative humidity, these polymer resins already are in the pore condensation phase, right? By a long time. So you'll have a lot of condensed water clusters in the pores of these materials, and these materials are amorphous, meaning that they'll have small pores, they have large pores, and especially small pores are probably already completely filled by then. So what you see is that during some of the higher pressure adsorption steps, you start seeing this dip. And that's an issue because, we don't know, because we can't measure, currently at least, what it is that is desorbing here. Is it water, or is it CO2, or is it both? And you see that, as you start to dose higher pressures or larger amounts of CO2, that these dips can become bigger. And this is an issue for the interpretation of the result. And I'll illustrate that in the following slide. So here we have the same dynamic profile. So what we normally do in measuring the uptake at a certain partial pressure is we just measure the difference between the plateau of the previous step. This is the mass difference, the plateau of the previous step, and the plateau of the next step. So you see this blue line here with the blue arrow, and that's how we measure the uptake of CO2 in a humid environment. And so in a saturated water saturated material. And what you get then if you do that is you get isotherms, obviously. So here you see a partial pressure on the horizontal axis and normalized loading on the vertical. And the black line is the adsorption isotherm in dry conditions, so 0% RH. And the orange line is under 55% RH. So this isotherm was generated with the method that I'm showing here, right? So we're ignoring this little dent here, and we're just assuming that this was only that this was CO2 or desorbing, and therefore we're only assigning the delta represented by this arrow to the CO2 absorption. But of course, we don't know if that's true. So it may be that this dent is caused by water desorption, in which case the CO2 would be fully responsible for this whole adsorption differential. And if you then plot the corresponding isotherm, it would be like this. And that's quite different, right? So we're talking about what the 30% increase at 1 bar. And most likely the reality is somewhere in between. But I just want to showcase this. Now, do we capture CO2 at 1 bar? Not really. So you might say this isn't much of a problem. Yeah, maybe that's true. At the same time, you can be in desorption conditions where you have higher partial pressures. So probably this is something that you would like to know. Then another issue, and this is very common with vacuum equipment, sometimes they leak. and what we see here is also a failed experiment. Again, the water sorption step, the CO2 sorption step, and what you see here represented by this dotted line is the target pressure. And this blue line here is the real pressure. And what is hardly noticeable, but is that here, there's the first CO2 step, and here is the second CO2 step. So I can see it on my screen, there's a minute increase of target pressure. But what we also see is that the ingress of whatever it is, at that point we didn't know what it was, is much larger than the increase in pressure that we want because of the CO2 dosing. So what in this case, what we figured out after a lot of trial and error, and I can tell you helium detectors are great at troubleshooting vacuum equipment, because without that we wouldn't have succeeded. But it was an MFC that was leaking. So it was a CO2 MFC. So actually this was just CO2 dosing in continuously, right? And only at the third, or actually the fourth step, the real pressure started to match the target pressure. So, this is not nice. And this just, if normally you can measure a coadsorption isotherm in maybe a week, but if you're troubleshooting, that takes weeks to months. Okay, so what you have is a long time to equilibrate coupled with a slight MFC leak, which basically gives you a failed experiment. And that's one of these headaches. This was also a nice one. What we see here is, again, we adsorb water first to saturate the material, and then we start pulsing in CO2. So you see here this very nice water adsorption curve, very nice CO2 adsorption curve. But if we now look up closely, so what we see here is that this was the target pressure of the water and also the average pressure of the water. It doesn't quite look like it, but it's about the average pressure of the water that we got into the system. And what we also see is that this downward trend here, this was CO2 pressure, and it actually goes below the water pressure. So that would mean that we're losing adsorbate, but we're at a deep vacuum. So, we can't lose it to the environment because mass doesn't tend to flow from low pressure to higher pressure. So, we didn't know what to think about this. And so what we did was a glass bead test, and we saw exactly the same. So, doing a glass bead test that confirmed that it wasn't the material that was doing something strange. It was just, we were losing gas. And in this case, what happened was that we had contaminants. So we had some adsorbent beads that had spread through the system, and they were stuck on a ledge somewhere, and they were not in the sample pen, so they were not contributing to the mass change, and therefore we had actually adsorption going on while there were no official adsorbents in the sample pen. And these kind of things is continuously going back and forth is what makes this very challenging. So then, one can ask, can't we do any better, right? And I think the answer is yes. And recently, machines have come to the market that operate not at a vacuum, which makes life really much easier. They can have different drawbacks, but in general, they're much easier to operate, and I think that's very helpful. And we're also working with machine or with instrumentation manufacturers to really close that mass balance much better, right? So to discern much better between water and CO2 adsorption isotherms. So that's ongoing work. Now, kind of a switch gear towards understanding the mechanisms. So, okay, we've now seen that polymer resins, they respond in a certain way to water, but the question is why? And we started thinking about this in about 2020. And first, we based ourselves on the literature because if you start in a field, that's usually a good starting point. So what the literature had observed is that primary and secondary amine functionalized sorbents, they show increased CO2 capacity under wet conditions in virtually all cases. So that was a starting point, and kind of our measurements confirmed that, right? And then the literature suggested that there would be 3 enhancing and or inhibiting mechanisms for CO2 absorption under humidity. And the first one was side blockage. So, I mean, this goes against the notion of enhancement, but if you have water adsorbed, water hydrogen bonds with amino groups, so it forms clusters on these groups, and in that way it can inhibit CO2 adsorption. And then there was another mechanism that was very often reported in the literature, and that was the difference in stoichiometry and in the speciation under dry and wet conditions. So what the literature suggested is that in dry conditions, so 2 amino groups were needed to capture CO2 molecule because they form ammonium. This is ammonium group, carbamate. So not carbonate, but carbamate, right? This is carbamate. And then what the literature also suggested is that in wet conditions, they would form ammonium bicarbonate, right? And that could happen because there's water, so CO2 can dissolve and form bicarbonate. And then finally, there was a suggestion that in dry conditions, so what can happen also is that CO2 forms carbamic acid. So you see here a paired carbamic acid, the carbamic acid pair. And then each CO2 molecule also uses only one amino group. And then under wet conditions, there were studies that suggested or confirmed that carbamic acid can also be stabilized, for instance, by water, in which case the stoichiometry doesn't change from CO2 to amino group, but the heat of adsorption may change. So this was what was suggested then. But of course, we didn't stop at just doing isotherm measurements. As I already said, the working horse are for the adsorption science are breakthrough experiments. So we did that too, and we did that for our resin under different humidities and at 25 degrees. And what you see here are the breakthrough curves. And what you see is that actually most of them align quite nicely. So the green one is the breakthrough curve in dry conditions. And then we see here a couple of wet breakthrough curves, the red one, the orange one, and also here the blue one. But you see the blue one, the blue breakthrough is quite a bit slower than the other ones. And that was also confirmed in the gravimetric methods. So there you can also just derive the diffusion coefficient or the LDF constant. And we saw indeed that these were much lower at 30% relative humidity. And we thought about this in many ways, and we tried to link this to the stoichiometry, but we couldn't come up with a reason why that would be the case. We just couldn't see why at 30% RH, the kinetics of the adsorption will be slower than at in dry conditions or at the other relative humidities. So we went to collaborators, and this was the Reimer group, and the work was done by Ah-Young Sung. And these guys are extremely clever. So they use solid state NMR to look into materials. So they can tell you what is happening inside a material and how adsorbates are binding or are adsorbing onto adsorbents. And that was exactly what we wanted to know, because our question to them was, do you form or do you see different species, so different ions and different speciation at 30% RH than at the other RHs or at dry conditions? So they worked on this for a long time, and this is also a study that easily takes a year, but in this case even longer. And what they did find, I'm not going into detail of the graphs, but what they found is that ammonium carbamate is formed at low CO2 pressure, or actually at all CO2 pressures, but under dry and humid conditions. So remember that here I said that under wet conditions, ammonium bicarbonate would be formed. But they said no, it's ammonium carbamate. They also said that at very high CO2 pressure, but really high CO2 pressure approaching 1 bar, some carbamic acid was witnessed, but conclusively no ammonium bicarbonate is formed. So, they looked at the material from different angles and in different manners, and they could not identify ammonium bicarbonate. That is, I think as close to something conclusive as can be is what they did. So this kind of put our worldview of coadsorption a little bit upside down, because then the question was, then what, right? We had a hunch, and that hunch was confirmed. So this is another graph that I'm showing here, and this is of NMR relaxometry. So it's a different NMR technique, but basically what they can do with this is identify where free and where bound water sits in the molecule. And they can also look at the mobility of that water, and that also says something about the mobility of the polymer chains in this case, because this was done for levity as well, so polymer resin. And what they showed is that the mobility is very different for 30% RH, very different than for 80% RH, or for activated, which is basically just dry CO2 or dry material, sorry. And the reason for that is swelling. So, had we been polymer chemists, then we would have probably understood quite quickly that resins swell. CO2 can be a solvent for resins, water can be a solvent for resins, but both make a material swell. And you also have to remember that these materials are amorphous. So if the partial pressure of an adsorbate is very low, what you will have is a material that looks like this here on the very right. So it's kind of shrunk and shriveled into a very dense little bead with basically nothing in there. There's nothing in there to keep these pores open. And as you start to dose water, so for instance here you see that, I mean the water just pushes the pores open. So that means that it generates access to pores that were previously closed. And that is exactly what is happening with these polymer resins and why water enhances CO2 adsorption. So if you have only CO2, then the CO2 needs to do all that opening way, right? It's like blowing up a balloon. If you want to blow up a balloon, you need to put quite a lot of force on your cheeks and your mouth to blow up the balloon, right? So if you have only CO2, then the CO2 needs to do all that work. If you have water, then water does that work for you, and actually, because the whole mechanism of water sorption, including pore colonization, etc., monolayer, multilayer adsorption, it opens up pores that were previously closed, and it just rearranges the polymer change. So that our current understanding is that is what causes the enhancement. And okay, now I need to jump right back to the very first slide. I'm going to do it. Hold on. This one. That also explains why the enhancement is really only observable in the very low CO2 partial pressure range, because at higher CO2 partial pressures, the CO2 itself will have solvated the material already. So the presence of water doesn't help anymore, because the CO2 will have already blown up the pores. So this is our current understanding. And the nice thing about science is that, a paradigm is true until a new paradigm presents itself. So it may well be that we're proven wrong in a couple of years from now. And we'd be happy to, because that only means that science has further advanced. But this is how we believe that the water helps the CO2 at this moment in absorption. Okay, sorry, I have to go back. Okay, so we were here, right? These polymers, they swell. Of course, we wanted to check this ourselves. So, okay, somebody can have like the greatest machine and look inside the materials, but sometimes we are also just pragmatic, and we just want to do a visual observation of the swelling. Normally, people do gravimetric measurements for swelling, but then you just get your isotherm. So we wanted to do a visual observation to kind of corroborate that. And you see the results here on in this left plot. So for 4 different relative humidities, we measured the percentage growth, and we did that all in triplicate, and therefore you see error bars. And this is not a very sensitive measurement, so the error bars are quite large, but the trends are as expected, and they're also pretty significant. So at low relative humidities, you get only a very small amount of growth, and as the relative humidity increases, the growth also increases, and that's what we expected. And with levitate, we see a percentual volume growth of a maximum of about 10%, and the NMR predicted 8%. So very close. So it kind of corroborates what the NMR had discovered, and we did that with visual experiments. And what is also nice, if you then kind of plot here the water adsorption isotherm, so that's the blue line that we see here, and on the secondary axis you plot the percentage swelling, then the two correspond really nicely, don't they? So for the ones that are not very familiar with water adsorption, so what you see first is that you start with a monolayer water adsorption. Then very quickly you start to form multi-layers, especially with this material. And then we have this whole regime here where you have a lot of multi-layer formation, and that gradually goes into pore colonization, right? And then with these kind of resins, that we roughly say that starts at about 60% RH. So that's good. So the swelling measurements, they corresponded very well to the isotherms. So okay, problem solved. We now know what causes our enhancement, right? So it was not the chemistry, but it was the swelling. So it was a physical concept. And now kind of briefly, moving towards the third challenge. So then, okay, how do you model that, right? Because, well, how we normally model things is using isotherms. And for chemisorbents, very often we use a Toth isotherm. If you're really good at fitting, maybe you can fit them well with a Langmuir isotherm. But often the affinity in the Henry regime, or the affinity and the steepness of the slope in the Henry regime is too steep to kind of fit that nicely with the Langmuir. So that's why people very often use the Toth. And I mean, the Toth isotherm is nothing else than a Langmuir isotherm, but then including this parameter tau here, that supposedly represents surface heterogeneity. So a normal isotherm is a function of the pressure of the CO2 and of the temperature, and then here you have the Toth isotherm. So what we did is then, we said, okay, we want to make this a function of relative humidity. We know or assume, and this is becoming more of an assumption than of knowing, because I think the more we know, the more we also know that it's not completely true. But we assume that water isn't affected. Water sorption isn't affected by the CO2 sorption, and it is, but not drastically or not dramatically. Okay, but that's actually a nice next research topic. And then we adjust the parameters to be a function of temperature and relative humidity, right? And for the ones who know these kind of isotherms, and the parameters know that each of these, so the Q indefinite, the B term, and also the tau term, they have another function another equation that determines their relationship with temperature. And what we then do is try to adjust these isotherms so that they don't only vary with temperature, but also with relative humidity. Now, I don't have the time to go into these coadsorption models in detail. That would take a whole lecture in itself. But I did want to show a couple of example papers. So there's work by Hefti and Mazzotti, by Stampi-Pombelli et al., Elfing and Sainio and Young et al. So if you're interested, I'll give people a minute to make a screenshot, and yeah, and you can go look for the different models. What I did want to say is that you need to be very careful with what you're with which model to select, and also what you're using, because you need to make sure that your model is suitable for the purpose that you're using it for. So for instance, the model that we presented in the Young et al. Paper was actually for, it assumed that the enhancement was because of stoichiometry and other mechanisms that we now have confirmed are probably not true, at least not for the materials that we are using. So they may be true for other materials, but please confirm that before you use these models. I think that's the message. Don't just go and select a model because it's simple or because you like it, but make sure that it has some physical meaning, because otherwise you'll be modeling something that doesn't make sense. Now, to end up with, so the reward, right? I mean, we measure these coadsorption isotherms. It takes years. It's extremely difficult. Very few people that do it. That's why hopefully more people will start doing it, because that's exactly what we need for CO2 capture. But the reward is this. So once you have all that information, so you have your isotherm models, you have your mass transfer rates, and we can measure these also in wet conditions, right? With breakthroughs, but also with our gravimetric balances. It just gives a lot of useful information. And by the way, we've shown before that mass transfer rates are more important, for instance, for a direct air capture process than the isotherm, right? The isotherm is not unimportant, but mass transfer rates the results are more sensitive to mass transfer rates. So then you put your bed design in and the cycle design. You put it in your cyclic adsorption model. You solve the equations, the mass balance, the heat balance, and momentum balance. And then out comes purity, recovery, energy consumption, and productivity, right? And if you do that, for instance, for levitate, something really interesting is then that you can do that for different climatic conditions for direct air capture. So here we show again the productivity and the specific work equivalent. And what you see, and that's just great about these kind of materials. So as your productivity goes down, your specific work, goes up, your specific work goes down. Well, I'm sure that most adsorption people would love something like this, because usually it's the other way around. But not with the materials that we have, and of course, if you push it even further, then you start to see a slight Pareto front here in this region. So yeah, there is a trade-off at some point, but in the beginning it just all goes down. So we did this for the Gobi Desert because it's nice and cold there and it's not very humid. So we wanted to know how the system would perform there. And then also we did it for Iceland because the only solid sorbent duct plants that operate nowadays are in Iceland. And I think that the difference in this is done for the exact same amount of process conditions, and the difference is striking, right? And I think one of the most important insights is that, for instance, in Iceland, you need to draw much less of a vacuum because you have much more humidity, and the humidity desorption already creates a driving force for CO2 desorption. It artificially lowers the partial pressure of the CO2. Therefore, you have more of a driving force for desorption. Less so in a very dry environment like the Gobi Desert. So there you need to draw a lower vacuum here of 0.25 bar. Of course, you don't have to stop with the Gobi Desert in Iceland. You can do that for the whole world. And then this is a result that one of my current PhD students has produced. And she's made a world map for a direct air capture solid sorbent process with updated levitate isotherms, by the way. This is for levitate. And then you can start to investigate where it makes more and where it makes less sense to actually do direct air capture. And levitate is just one material, but you can do this for other materials too, because it may well be that different materials perform different in a variety of conditions, and maybe in one climatic condition or one zone, material X may be better than material Y or material Z. But that is the kind of information that we cannot currently predict because we're simply lacking the coadsorption data. And I think that's why it's so very important that we do much more coadsorption. In our lab can, like I said, a full set of isotherms for one material easily takes a year. So we can only do so much. So it's also an invitation for other labs to start investigating coadsorption much more. Take-home messages. Measuring water CO2 coadsorption is very complex, especially at very low CO2 concentrations, and we need improved methods. And it's one of the things that we're working on with our industrial collaborators. It is critical to get this right, though, to design optimal sorbent process combinations for different flue gases and different duct climatic conditions. And for polymeric resins, water influences CO2 uptake via swelling and not via stoichiometry. And this may need coadsorption models that are different from other functionalized sorbents. So, again, be mindful which model you use for which material. And we can model water CO2 coadsorption. There it is again, but be careful to ensure that the models are applicable across the use range, in any case, the use range, and are representative of the physical and chemical phenomena that are really happening in the material. And with that, I'll be very pleased to take any questions. And I hope you've enjoyed this. And by all means, reach out. My email address can be found on the university website. I'm on LinkedIn as well. So if you have any questions about the lecture afterwards, then feel free to reach out. Thank you very much. Bhupesh, shall I stop sharing?
No, you can leave the screen on. We have a couple of questions coming in.
Okay.
Yeah, I'll send some of the questions towards your way. So we have a question from Clinton Obang Manu. How does the pre-humidification affect the chemisorbed products on your sample?
Yeah, so that's yeah, it doesn't. So we see the exact same chemisort product, ammonium carbamate under dry and humidified conditions, and that is contrary to what the literature has always said. So the literature, at least for our material, is wrong.
Okay, definitely. Yeah. And we have a few other questions coming in. We have a question from Tomas Alexandrex. There's the peaks in slide 12. I think that's probably about the devious measurements that you do. Are the peaks only due to, do they come around only while changing the CO2 concentration? Probably the dips that you show in your
Yeah.
devious uptakes. Is that only
These.
during changing these ones?
Yeah, and you only see it at higher CO2 pressure. So I mean, let me try and interpret this for you. So here's a CO2 step, here's a CO2 step, here's a CO2 step, here's a CO2 step, here's a CO2 step. So these are very small, right? These are all in the hundreds of ppm CO2 range. And then here comes a bigger step. And then finally, here we're probably at tenths of bars, sorry, tenths of bars, not tenths. So yeah, at higher pressures, you start seeing these dips. And you also see that in the divergence between these two orange lines, right? So here we're at 10 millibar here. So from 10 millibar onwards, they start to diverge. But before that, you don't see these dips.
Okay, yeah. It's an interesting material. We also have a question from Tim Neeson at the TU Delft. Do you have any thoughts
Tim.
on the?
Hi, Tim.
Yeah. Do you have any thoughts on the influence of humidity on absorption kinetics?
Yes. Yes, I do. I have a slide on that. Let me think. Okay. I'm going to very quickly exit this and then make a slide that I hit. I'm going to make that slide visible. So here you see the diffusion coefficient for CO2. And this is for levitate under different relative humidities. So it follows this parabolic function. It follows a polynomial. And this diffusion coefficient was, by the way, it's a lumped, so a lumped effective diffusion measured in a gravimetric balance. So our machine records the mass uptake every so many seconds or milliseconds, whatever. And that's how we can extract effective diffusivities. I mean, it's as good as it gets.
Okay, and I have a follow-up question on this. So this would, of course, affect our productivity as well, right? Like, even though the loading increases, the mass transfer changes. So there's always a trade-off or something.
Yeah. Yeah, it does. The funny thing is that what you do see is that, although there's a variation, you see that the diffusion coefficient is between 1 and 2 to the power of minus 12, right? So it's also not the case that the difference is massive. We've tried to vary the diffusion coefficient, in our cyclic models between these values, and you don't see that much of an effect. So that's kind of reassuring. So because we've also been wondering, do we need to make the diffusion coefficient or the LDF parameter a function of humidity? And we can. I mean, we have the function right here, right? So instead of putting in a value, you put a function in your model. But at some point, you also don't want to overburden your model with loads of different equations. And yeah, we felt that taking an average was good enough.
Perfect, thank you. And we have a question from Shanmukh Ravaru here at UFA. Their question is, do all the primary amines show the same enhancement factor, or would the enhancement factor also depend on the role of the support structure?
Yeah, no. So you have to measure this for every material. And that's why I said we can only do so much. I mean, we have colleague Susana Garcia and myself in this lab, and we have to two machines now that we can measure this kind of stuff with. So, by all means, other labs also go and do this, because we need that data. But don't only measure it, also try to to confirm the mechanisms, because that's where we went wrong in first instance, and that's maybe even more difficult than measuring the enhancement.
Okay. And Nicholas Wilkins had a question. We were talking about swelling of luetate in the presence of water. Does it also swell in the presence of CO2? And how does it compare to, let's say, swelling in the presence of water?
Yeah. Yes. So absolutely. So both CO2 and water are solvents for amine functionalized polymer resins. So not necessarily for every polymer resin, but for the amine functionalized ones for sure. But the nature of the adsorption is very different, because water condenses at room conditions, at least if the relative humidity approaches 100%, and CO2 doesn't start condensing until close to the critical point. So the amount of swelling is different, but they both have the ability to solvate polymer resins. Yes.
Okay. And on the same note, we have one more question from Thomas. Do you guys only study coadsorption of CO2 and water on luetate, or is there interest towards other resins as well?
I mean, we are interested in different resins, and just for the heck of it, we recently did the swelling experiments also on Purolite. I mean, we measure different resins and also different materials in our labs. We also look at MOFs, coadsorption, and others as well. But we also did, for instance, the swelling experiments with Purolite, and that swells much more than Levity. So that was an interesting finding. That was just a gag. I mean, the results were too crude to publish for him, but so. Yeah, we look at different resins and at different materials in general.
Okay. And we don't have any other questions on YouTube, but maybe before we close, we could ask a couple of high-level questions. What do you think about, let's say, the oxidative stability of these materials, the scalability of these resins? Is there a challenge there, or what are your thoughts on that?
I think that's a really good question. The scalability is great. So this is just, these materials are and have been produced for a long time, mostly for use in water, for water treatment. So in the water sector, not per se for CO2 capture, but they are now as well, or at least they're marketed as such. The scalability is great. The oxidative stability is unknown to a large extent, and that's an issue, because not only does your material become less effective after time, but we know from solvent-based carbon capture that oxidative degradation also releases volatile gases. So ammonia is the most important one. I mean, you don't want a capture plant to emit ammonia. I mean, not more than any other industrial plant is allowed to, right? And also for direct air capture plants. And we don't know very well how much they degrade. So I think there are people at Georgia Tech and the Lawrence Livermore National Lab that are doing really great work at degradation of materials. But again, they are among the few. And there are so many materials, and there's so much to understand there, that we can definitely use more people looking into that. Yeah.
Yeah, true. Yeah, definitely. I think those are the questions we have. Thank you for the wonderful discussion, Dr. Mijndert. I'll pass over the screen to Nick Wilkins again.
Thanks.
Okay. Thank you, Dr. Mijndert Van der Spek, for your presentation, The Complexities of Water Carbon Dioxide Coadsorption onto Chemisorbents for Carbon Capture. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed here today will be a useful resource for the adsorption science community in the future. The next confirmed IAS webinar will be given 2 weeks from today by Dr. Marc-Olivier Copin on March 26th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed, LinkedIn page, and through the IAS mailing list. For that, we thank you for joining us and hope that you'll join us again soon.